Welcome everyone to the continuation of the series on the chapter of kinematics. So today we will be studying the topic of non-uniform axial motion of a particle in one or more dimension. So in the previous videos we have been mainly focused upon cases when the acceleration of the particle has been a constant, and because of which the acceleration of the particle is because of which the equations which we take are more or less same only, like the equation b is equal to u plus at, b square is equal to u square plus 2s, and x equal to ut plus half at square. So these are the equations which we have been using, and these are used in the cases of axial motion. Now our focus should be what if the acceleration is not a constant. So what are some cases in which acceleration of a particle is actually varying, or acceleration of a body, let's say, is varying. So the acceleration of body can actually vary with time, and it can vary as the particle moves or as the body moves. Now in the last video we learned that, let's say, if a body is released from some height above earth and it's close to earth, then its acceleration is a constant which is equal to g. So it's a case of uniform accelerated motion. But in the same case, if we are able to take the effect of surrounding air on a ball falling from some height above earth, then that would become a case of non-uniform accelerated motion. That means there are some other forces which would be at play in addition to the Earth's gravity. So this would lead to the acceleration of a body varying with time. So we must learn how to apply our equations, or how to approach such questions which involve these situations. One more case can be, let's say there is a block, as block is moving on a surface. Now we know that a lot of surface have friction and it is varying. Now let's say the surface which we are considering has variable friction as the block moves on it. We are considering a block, and initially the surface is really rough, and as the block moves in a forward direction, the roughness, it gradually goes down. So you would expect that the deceleration which the block is experiencing would also go down as the block is moving forward. No matter, the block would be slowing down because the surface is rough. As the surface is rough, the block goes in forward direction and it is slowing down. But what if the roughness itself is going down? That means that the acceleration which it would experience would change, and that is what we are focusing on, not how it is changing, but whether it's changing or not. And if it is changing, what should we do about it? So the problem comes that the main problem is that the equations which we have been using are not applicable for non-uniform cases. And this is a common mistake actually. Then even if acceleration is non-uniform, people tend to use the equations which we know, because we have practiced mostly that way. But we have to be careful in such questions that, okay, if the question is asking that A is a function of something, A is a function of time, then the question is indicating that, okay, acceleration is going to change and you better avoid the equations x is equal to ut plus half at square, which we have been serving you very well. So what we do is that let us take an example, and before taking an example, let us see this particular idea which are in the boxes. These ideas tell us that if acceleration is a variable of time, we use a equal to dv by dt, and if acceleration is a function of position, then we use a is equal to v dv by dx. These are the main ideas which we have to keep in the mind, and these are important. So whenever you see that the acceleration is varying with time, then simply use A equal to dv by dt and try to use it. And if acceleration is varying with position, then try to use A equal to v dv by dx. And the main idea is that why it is not a strict rule that you have to use it no matter what happens. Let's say if acceleration is a function of position, it's not a strict rule which is saying that okay you have to use it. It is suggested that in most of the cases you use it, and the reason is that in most of the cases, when the cases which are suggested are written here, these suggestions in the boxes try to reduce our time in doing the calculations in most of ways. So let us see. So the first example is x is equal to t cube. So we have to find the velocity and acceleration of the particle at t time. So it is given to us that the position of particle is varying as third power of time, x equal to t cube. What would be the acceleration and velocity of the particle at some t time? So instead of acceleration, we are asked acceleration. It is instead of being given provided us acceleration of the particle, we are given the position of the particle. So what we are supposed to do is that we are supposed to remember the basics which we started velocity with. So when we started velocity, we first begin with average velocity at the instantaneous velocity, which basically defines the velocity of the particle as a single differentiation of the position of a particle. So you would easily guess it, okay, if I differentiate the position of the particle, I would get the velocity of the particle, and the position of the particle is t cube. So the velocity of the particle would be simply 3t square. So which it is given here, velocity is 3t square. Next, what is the acceleration of the particle? The acceleration of the particle is calculated using differentiation on velocity. So if we differentiate velocity of the particle, we would get acceleration, and we have already calculated the velocity of the particle as 3t square. So the acceleration would be simply 16. Next, a particle moves as per v equal to at square. A is a constant, so this particular A is a constant. It's not acceleration actually. Find the displacement of a particle and its acceleration at t time. Okay. So let us first write what we are required. So we are required the position of the particle, and then we are required the acceleration of the particle. It is given to us that velocity is at squared. It is given that velocity is equal to a into t square. Now this a is a constant, and what we are trying to use is this expression. This expression says that when x is differentiated, then we get velocity. If velocity is differentiated, we get acceleration. If acceleration is differentiated, we get integrated, we get velocity, and if velocity is integrated, we get x. So we are in the middle of this diagram, and we have to go forward and then we have to go back. Then if we go back, that is we integrate, we would get the position of the particle or the displacement of the particle, and we move forward, we would get the acceleration of the particle. So this is a very simple rule to understand. So let us first try to find the displacement of the particle. So integrating. So here what are we going to integrate with? So that is the important point which we are supposed to learn. Okay, we know that we are going to integrate. So what are we supposed to integrate with? So there are two approaches. First approach is whether we understand what are the variables in the equation. So you would easily know that their variable is t squared. Okay, then we can already integrate with dt. So if we can already integrate with t, then we put dt in the LHS of the equation and dt in RHS of the equation. And this is the one approach of doing the question. And second approach which you can say is that we open v. That is we write the v expression as dx by dt and take dt to the right RHS of the equation. That would give the same result. So integrating, we know that integrating gives us the displacement. So if we integrate v dt from some position, let's say x1 to x2, then it will get the displacement, and let's say time is going from 0 to t. So the displacement of the particle delta x is equal to integration of at square. Now a is a constant, so it comes outside, and integration of t square dt from 0 to t. So delta x, we already know that integration of velocity with respect to time from x1 plus x2. This is basically a displacement of the particle. So that's why it is delta x. So delta x is equal to a and integration of t square. So if you remember it, it is actually t to the power 3 upon 3. And then we would substitute the limits. And the way to substitute the limits is the final limit minus the lower limit. Lower limit is 0, then that expression would simply be nil. So this is the displacement of the particle. In the same way, we are supposed to find the acceleration of the particle. The acceleration of the particle can be found by differentiating it. So we would say what is dv by dt, and the velocity is at square. So d by dt of at square is equal to a into t square, the differentiation of t square, which is 2t. So this is 2at. So that is the acceleration of the particle at some t time. So this is what we are looking for: acceleration of the particle and the displacement of the particle. Okay. So let us try to clear this board. So in the next question we would be discussing that how are we supposed to solve a new idea. So the next question is that body follows the path x equal to at plus bt square plus ct cube. Find the speed of the body at 1 second. Okay. So the question now is, so yes, we are trying to let's do the next one. So in the next question, we have a body which follows the path x equal to at plus bt square plus ct cube. Find the speed of the body at t equal to 1 second. So x is equal to at plus bt square plus ct cube. And we are supposed to find the speed of the particle at 1 second. So let us simply differentiate it. If we differentiate it, we get the velocity. So this is a plus 2bt plus 3ct square. This is the velocity of the particle, and we have to find the velocity at t equal to 1 seconds. So we substitute t equal to 1 in this expression. We would get a plus 2b plus 3c. So this is the velocity, and if we take the magnitude of velocity, that would be the speed of the particle. If at all any of these variables turn out to be negative, then it would simply be the speed of the body. Okay. Okay, so let us jump to the next question. So in this particular question, let us try to read this. So the retardation of a particle is a is equal to minus kx, which is mentioned above. So in language it is written like it is moving in a straight line, and its retardation is proportional to its distance which it has traveled, or its displacement. So find the velocity of the particle in terms of x when the initial velocity of the particle is v0 and initial position is 0. So the language which is given here is that the velocity of the particle is proportional to its displacement. Since the retardation of the particle is proportional to its displacement, so a is proportional to x and the proportionality constant is some k. So it is given to us, this expression is given to us, a is equal to minus kx, and we have to solve it further. So okay, let's go. So acceleration is given as minus kx, and we are supposed to find the velocity of the particle. So this is where what we have learned we can apply. So in the previous two questions we were simply integrating and differentiating and following some simple rules, but now we can apply what we have learned in this particular topic, that if acceleration is actually depending upon the position of the particle, then we must use the expression acceleration is v dv by dx rather than using acceleration is equal to dv by dt. So we have substituted acceleration as v dv by dx, and we'll try to integrate it. Now v dv is equal to minus kx dx, taking the dx to the RHS. Next, let us integrate the expression, and we have to put the limits to integration. So initial velocity is v0 and initial position is 0. Initial position is 0, initial velocity is v0. Let's say we want to find some final velocity v and some final position is x. So integration of v dv is similar to integration of x dx, which is x square by 2. So we would get x square by 2 and integration v0 v square by 2. We are integrating v, this would be v square by 2, initial velocity v0 to some final velocity, and similarly this expression kx integration would be simply kx square by 2, lower limit is 0, and this would turn out to be v square minus v naught square by 2 is equal to minus kx square by 2. So this is v square is equal to v naught square minus kx square, and v is equal to square root of v naught square minus kx square. So the velocity in terms of position which we were requiring. Next question. Acceleration of a particle is a function of velocity. This is a good one. Find the distance covered by the particle before its motion ceases, before it stops moving. So, rather than focusing too much on the expression of the equation of the question, that okay, this is a quite complicated looking expression, right? A is equal to minus k square root p. Acceleration is given in terms of velocity. It does not fit any of the cases which we are looking for. Let us try to read the question further, and this gives us a bigger lesson that whenever there is a question which you think is which does not fall under the ambit of what you have learned, or is not completely falling in the blocks which you have designed, then it's probably it's probably advisable that we try to go what more is given in the question. So here it is given that you have to find the distance covered by the particle, and yes, it may seem that okay, how to find the distance? There is no expression of position whatsoever in the question as of now, but it still gives us a hint which can be understood quite easily, that we have to think in terms of position of the particle, right? That means that at least you won't think in terms of time of the particle, and it's just same like saying that okay, when you have a question of uniform acceleration, and in that question you are trying to find the distance covered by the particle, acceleration is given, velocity is given, then you won't write v equal to u plus at, right? And you won't try to use the equation x is equal to ut plus half at square and so on, because they require time, and time is nowhere given in the question. So the hint which we take from this question is that try to think in terms of x. So there is only one equation which is in terms of x which we know, which we are actually circling right now. So the equation which we have, which is in terms of x, is what we already know. And the equation acceleration is equal to v dv by dx. Now we don't know how the question would turn out to be, as it is with every question, but we know that okay, at least we don't have to use a is equal to dv by dt, that we are to specifically use a equal to v dv by dx, and it would give us a result better in that way, where acceleration of the particle is given as minus k square root v, and this is equal to v dv by dx. So this is minus k dx is equal to square root v dv. So one square root goes over here, and now we have to integrate. So this dx, which is in the denominator of the expression, it comes to the LHS kx dx is equal to square root v dv. Now we integrate. Now it looks pretty simple, right? Now we have to travel some distance s, initial velocity of the particle, let's say some v naught, and finally the particle would be stopping. That is what is the question asking from us. Find a distance covered by the particle before its motion ceases. Ceases means that the particle is stopping. Initial velocity is v naught. So you would say that minus k x square by 2, and integration of square root v is v ki power 3 by 2 and 2 by 3 v naught. So this would cancel out, So I just repeat the calculation which I have done. Calculation is that we integrate kx dx, which we know, it would be x square by 2, limit would be 0 to s, and k is a constant, is outside. Integration of v की power half is v की power 3 by 2 and 3 by 2 in the denominator. Now finally the particle is stopping and initially the particle is moving with v naught. So this is k s square by 2. 3 by 2 would be 2 by 3, v power 3 by 2. So first we would put 0, and then we would put v naught. So when we are substituting v naught, v naught power 3 by 2. So k s square by 2. Okay, right now there is no x actually over here. If we notice over there is no x here in this expression. So there would be no x here also, right? And this x won't be there also. This would simply come out to be s, and this would come out to be minus 2 by 3 v naught की power 3 by 2, and negative sign also cancel out. This implies s is equal to 2 by 3 v naught power 3 by 2 by k. So what happened is that we mistook this dx over x as x over here, and then we wrote dx again here. So this caused one more x to appear over here, which it wasn't there actually. So we removed this x from this expression, which turned this expression into simply k dx. The integration of k dx is simply kx, and when we put s into x, then it would be simply s, and there would be no 2 in the denominator, and this would be a final expression. So only the integration of RHS was required. LHS was pretty simple actually. So this is what we wanted. So this is the distance moved of the particle, which was moving with an acceleration which is proportional to the square root of the velocity of the particle, the negative sign. Okay. So let us look towards the last question of our idea. The last question is the velocity of the particle moving along the direction of x-axis varies as v equal to alpha square root x, where alpha is a positive constant. Particle is at origin at t equal to 0. You have to find the velocity in terms of time, which looks quite easy enough. We would simply put v equal to dx by dt and would integrate. Acceleration, we would differentiate the velocity in terms of either x or time. And we have to find the mean velocity of the particle for first estimator. Mean velocity means that we have to find the average velocity of the particle for the first estimator it has traveled. That means that it has traveled some estimator. What is the average velocity of the particle when it has covered that particular distance? That means we would be trying to find the time taken by the particle to cover that distance. So we know that v is equal to alpha square root x. V is equal to dx by dt. So square root x is in denominator and dt over here, and would simply integrate it. Integration of square root x is simply x square root x and half and we are going to travel to some distance, right? We are traveling to some distance, let's say x, and times some, let's say t. So this is some alpha t. This implies x is equal to 2 alpha t squared, or alpha t by 2 squared. So x is equal to some alpha squared t squared by 4. We want to find actually the velocity in terms of time, right? Okay. So right, we will just differentiate this expression in terms of time. So differentiating this expression, differentiate with respect to time. So now as velocity was given in terms of x, it was not actually directly possible to evaluate position and velocity in terms of time. So we calculated the position first. So after calculating the position, now we are trying to find, we are going to be coming back to the velocity of the particle. So we will differentiate it. So differentiating the position of the particle with respect to t would get velocity, and this would come out to be alpha square t by 2. So this is pretty easy differentiation. Next, what is the acceleration? Simply differentiating it. So this is part A. Differentiating velocity, let's say we differentiate velocity with respect to x only, dv by dx. So this would be 1 by 2 square root x into alpha. The power of x is half, the half comes here, and the power of x is subtracted with 1, so that would be x to the power minus 1 by 2. So it is square root x in denominator, and alpha remains as is. Now to find acceleration, we can say that v dv by dx is acceleration. Velocity is alpha square root x into 1 by 2 square root x into alpha. So this goes out to be alpha square upon 2. So this is the acceleration of the particle, and as you can see, it's a constant. So it turns out to be a case of uniformly accelerated motion. Now what is the average velocity for the first s meter which Anna has covered? It would cover s distance in alpha square t square by 4. If we put s in the equation of position, so this is the time it would take to cover s distance. So this would come out to be some 4s by alpha square root, that is t, that would be 2 by alpha square root s. And we have to calculate the first mean velocity for first s meter. That means we have to calculate it in terms of s. So average velocity is simply s, that is the distance which we are going to cover, and divided by the time it has taken to cover s distance. That would be 2 square root s by alpha. The reason for which we calculate the time beforehand is that we were to calculate the mean velocity of the particle in terms of, we were to calculate mean velocity in terms of s. That means we don't need time. So if we don't need time in the last expression, that means we have to eliminate time in the last expression. And to do that, what we did is that we found the time in terms of s, and then we substituted time as an expression of s in the equation of average velocity, and we got our answer, which is finally alpha square root s by 2. This is our average velocity. So this is the idea which we started with, and that is the idea of non-uniform acceleration. And the last question turns out to be a question of uniform acceleration. So as you can see that in non-uniform acceleration there is no one single approach to do a question, and that is the one thing which we can take away from this idea, that we have some what we say we have some check boxes for you, that if acceleration is in terms of time, then you can use a is equal to dv by dt. If acceleration in terms of x, then you can use a is equal to b dv by dx. And there is a line, there is an expression that if we differentiate x we get b, and then you get a. So that's a very good thing which we must try to keep in our mind. And the main idea is that in questions of non-uniform acceleration, we actually are not we are not looking towards the answer at the start of the question, and that is the main idea. In all the questions which we have already done in the cases of uniform acceleration, we know that okay, that this is the answer which we are looking for, and this is the majorly this is the way which we will be progressing with. In the cases of non-uniform acceleration, since it demands much more mathematical application in the question. So that's why there is no one single way to do all the questions. So we have to make do with the expressions which we are given with and the guidance which we are given with. So thanks for attending this lecture. In the next lecture, we will be starting with motion of particle in two dimensions and the projectile motion. Thank you.